The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Committee 14 has produced a guide document for securing, testing, and evaluating concrete cores for existing and new buildings. Really, the objective is to discuss some of the controversies. Hopefully, we can decrease these discrepancies. We have distinguished speakers today that would attempt to present some segments of this document. And now, before we start, I would like to ask Mike Bartlett to come over here and give us an overview of the content of the document.
Good afternoon. So thank you, Kyle, for giving me this opportunity to discuss the document. Many of you know there was a first edition of the ACI 214.4 document on core testing produced, I think, in 2003. So the second edition, which says R-10 for 2010, is now available. It has 9 chapters. The previous one had 8. The new chapter is the notation section, which is all jammed into chapter 2. Most of the document, there have been minor changes. There aren't wholesale changes that have been made to the document, and maybe that's actually a reassuring thing. The document was produced in 2003. It was a new thing, and people have been using it for a while, and so far we haven't had too many suggestions about things that really need to be changed. So there's some discussion of the variation of concrete strengths in structures, what you need to do to plan a testing program and obtain specimens and then carry out the test, analyze the data, and then actually the presentation that I'll be making primarily tries to make the important distinction between two things that people want to do when they take a course. Sometimes they're trying to see whether concrete, which was supposed to have a certain strength, and according to the cylinders that were tested at 28 days, doesn't have that strength. Chapter 8 talks about checking strength compliance in accordance with ACI 318 using cores. Chapter 9 is quite different, and it says, no, the ready-mix producer is no longer in the picture. This is a 20-year-old structure, and we don't have any information about the in-place concrete strengths, and to be able to do a structural evaluation, this is what we need to know. And so, kind of my experience before I became an academic was more focused on this kind of problem than this kind of problem. And I'd like to start my own presentation by really identifying why there's a difference between the provisions of Chapter 8 and the provisions of Chapter 9. As I mentioned, my particular interest in cores is trying to evaluate how much load an existing structure might be able to carry. Lions Gate Bridge in Vancouver was built in the 1930s. Specified strength of the piers was 3,000 psi, or about 20.7 megapascals. It was poured when the bridge was being considered for rehabilitation in the 1970s, and the 3,000 psi concrete had turned into somewhere between 6,000 and 8,000 psi concrete. So particularly for older coarse ground cements, if you've got a nice condition where hydration can keep on happening, using a number as an in-place strength that you've taken off a specification or a drawing somewhere would be very conservative, and that's really where I'm coming from. We're going to talk about 4 things here. First, as I mentioned, the difference between checking strength compliance in accordance with ACI 318, Chapter 5, and evaluating an existing structure. We'll talk a little bit about the basis of the provisions that are in Chapter 9. Since we came up with the first edition of 214.4, John Hansen did a survey of practice, which appeared in the 2007 ASCE Journal of Performance of Constructed Facilities. And it's interesting to see what practitioners were thinking in his survey. Worth noting that his survey was done before the 2003 version of the document was available, and then I'll make some quick conclusions. So perhaps the most important thing I want to leave people with is this notion that strength compliance, a decision about strength, involves 2 parties. So Here we've got a little simple matrix, the true state of whatever we're checking. It can be satisfactory or it can be unsatisfactory. The test results are never perfect, and so the test results can say that it's satisfactory or it's not satisfactory. If the test says it's satisfactory and it really is, nobody has a problem. If the test says it's unsatisfactory and it truly is not satisfactory, well, we kind of have a problem, but at least we agree about what the problem is, right? And so the really interesting cases come when the test gives you the wrong answer. So if you look in sampling and quality control kinds of literature, you'll see that there's something called the consumer's risk, where in this case the owner of the structure is being shown a test result that says the concrete is satisfactory, when in fact the test result is inaccurate, and the concrete strength is not satisfactory. There are some ready-mix producers in the room, and they have a risk too. And their risk is that the material they provided is actually good, but the test results, for whatever reason, are saying that the material is not good, and so the consumer is worried that poor quality material is going to be accepted, and the producer is worried about good material being rejected. And so the decision process must balance the risks of both the producer and the consumer. So what we do when we say in ACI 318, take 3 cores, take the average, and if the average is not less than 0.85 F times C, and the least strength is not less than 0.75 F times C, that's our way of saying, well, we don't think we really cheat the consumer when we make that decision, and we don't really cheat the producer either. Incidentally, there's a second round of optimization there. If you're trying to reduce these risks, then the answer is take more cores. And so the ACI core acceptance criteria, which have been around since, I think, the 1971 version of the standard, so about 40 years, okay, is saying that we think that this particular strength compliance issue, the balance is about where it should be. If we look at an existing structure, and this is the Umpqua River Bridge in Oregon, built in the midst of the Great Depression, the ready-mix producer is no longer there, and so realize, really, an engineer's assessment of the in-place strength should be trying to minimize the consumer's risk. It's actually unusual that a concrete structure is overly sensitive to the strength of concrete that's there. Yes, problems in a multi-story building, no argument about it. But if you're talking about a structure that's governed by a flexural response, changing the concrete strength could change the ductility of the response, but it isn't likely to change the strength all that much. And so for that reason, Chapter 9 of the document exists to say we're not worried about the producer's risks anymore. We want to make sure that the numbers that we're using are on the safe side. Whereas Chapter 8, which is checking strength compliance in accordance with 318, balances or recognizes 318's balance of those risks. Do not use Chapter 9 to check strength compliance. The very first sentence in Chapter 9 says, do not use Chapter 9 to check strength compliance, and I hope I've perhaps convinced you that there's actually quite a rational basis for that sentence being there. So quickly, what are we doing in Chapter 9? We're going to try to convert core strengths to in-place strengths. We're going to recognize that in-place strengths are uncertain for a number of values, and we're going to come up with an equivalent to specified strength. I should call it F prime C bracket equivalent, I think I can later, which we can use in customary resistance equations with conventional resistance factors and get the answer about right. There's the equation that relates the in-place strength. We're going to convert the in-place strength from the core strength, and we've got these factors in the middle which account for the length to diameter ratio, the diameter of the core specimen, the test moisture condition, whether it's as is in the structure, or whether it's been soaked for 7 days beforehand, or 2 days soaking, or 7 days air dry. There's something for drilling damage here that I think. This is a graph that shows the length to diameter ratio of the core on the horizontal axis and the core strength correction factor on the vertical axis to give you, for the strength of the core with the length to diameter of 1, the equivalent strength of a core that has the standard length to diameter ratio of 2. The ASTM C42 1927, that's the first edition of the core test standard in ASTM. And you can see that the results are not all that different from what's appeared in current condition, in more recent editions of C42. And the length to diameter correction factors depend on whether you soak your cores, whether they're standard in accordance with the current C42 practice, or whether they've been dried in air. But generally speaking, they fit the general trend of the historic numbers. Core diameter is a challenge. I think we agreed in the committee that there wasn't much difference between 6-inch and 4-inch diameter core strengths. But if you were doing 2-inch diameter cores, then we can say on average they're weaker than 4-inch diameter cores. This particular study is a little dated, but Yip and Tam did tests of 2-inch and 4-inch diameter cores. I think they were taking the averages of 5 moons of each from replicate mixes. And the range of strength correction factors vary between 0.6 and 1.5. So if it's practical, the document recommends that if you're using 2-inch cores, it's probably appropriate to develop correction factors from actual data that are representative of the mixes that you're coring. And I certainly know instances where some consultants have been able to successfully replicate the mix in a test lab that they're interested in looking at in the field, and to develop their own strength correction factors for small diameter cores. Soaking core before testing it causes lower strengths. It's believed that's because the outside of the core swells and the inside of the core, which isn't soaking, doesn't increase its moisture content, does not swell, and it restrains the swelling, and actually you get a tension due to the swelling on the outside across the inner part of the core. Conversely, drying the core in air for 7 days actually increases the core strength. So the ACI changed 7 or 8 years ago, maybe the 2004 edition, to have as drilled moisture conditions for testing cores, and really that's the one that people are probably using now. There's an issue about damage due to drilling, so the idea is that as you're drilling the core, potentially you're cutting through coarse aggregate around the perimeter. If there's any wobble in the core bit, then the perimeter is not perfect either. And so the core document says that you can take a correction factor for damage as 1.06. Once we know what these different correction factors are, we're going to get some in-place strengths, and as anybody who's ever been involved with core test results recognizes, those are going to be quite uncertain. The core strengths are going to differ. Often we have fairly small sample sizes, and so estimating the mean is a little bit tricky. Estimating a standard deviation or a coefficient of variation is even more tricky. In-place strengths can differ in a structure, so if you're coring through a slab is deep enough that you can cut your sample, your specimen, to get 2 test samples. Often the upper sample is weaker than the lower sample because the consolidation at the bottom is better than the consolidation at the top. The strength of the top concrete is more sensitive to curing than the strength of the bottom concrete is. This happens for columns as well, so many people know that if you're having an argument about a column, the producers always want to test at the bottom, and the representatives of the owner want to test at the top. Actually, if you test in the middle half, that's probably fair to both parties. The thing to note is that there's tremendous scatter in the empirical correction factors as well. And so not only are you trying to understand the uncertainty that's really out there, but you're also having to account for the fact that the various factors you're using to convert a core strength to an in-place strength have some uncertainty associated with them as well. So we can think about the standard deviation of the in-place strength, the overall standard deviation, being the sum of the standard deviation of the core strengths plus the standard deviation due to these empirical correction factors. And the empirical correction factor, if you haven't had to correct for length to diameter, if you haven't had to correct for diameter, then you can forget about any uncertainty due to those causes. If you haven't had to correct for moisture condition, that one goes out. And so actually the only one you'd be left with is the uncertainty associated with drilling damage. It's not exactly a 6% strength loss, and so that would that would increase the standard deviation from what you would get based on the core tests themselves. To get an equivalent strength to plug into a design equation that uses resistance factors that are customary in ACI 318, we don't want to take the mean strength of the in-place strength. We also want to recognize that actually the specified strength of concrete is roughly the 10% fractile of the in-place strengths. So what we're really saying is that if you specify a strength of 4,000 psi, then if you were to go out and at 28 days obtain specimens from the structure, if the structure has been properly cured, then actually there's about a 10% chance that the in-place strength is less than the specified strength. And so what we're looking for when we're looking at core test data is we're trying to find that number that we expect only 10% of the test results to be less than to use as the equivalent specified strength for evaluation. And so, as I said, this is essential because if you use the mean strength, this number is typically 85% of that number. If you're using the mean strength, then you should be reducing the resistance factors accordingly. I'm not sure if this is a big deal in concrete design, but the people, at least in Canada, that test structural steel coupons and then try to analyze the results get into trouble. So there's two approaches that are given in Chapter 9. One is to estimate a 10% fractile, either neglecting the uncertainty in the strength correction factor. So here we've got the 10% fractile being the mean in-place strength as derived from the cores minus a tolerance factor that we'll define on the next slide, times the standard deviation of the core strength. If the sample size is small, this is not very accurately captured, and the standard deviation is not very accurately captured. And to have some confidence that you really have got the right 10% fractile, you need to have a fairly large value of K. So again, please notice the negative sign before the K. As the tolerance factor K increases, the in-place strength that you would use for checking structural adequacy goes down. This equation neglects any uncertainty in the core strength correction factors. If you want to allow for that uncertainty, then you can include it as well, as described in the chapter. Here's the number of specimens that you're going to test on the horizontal axis, and you can see that the K value, if you're going to test 3 specimens, or I think that's 2 specimens actually, is a number like 2.5. If you're going to test 20 specimens, then the number is a number more like 1.5. And if your confidence level, how certain you want to be that you've actually captured the 10% fractile, 75% is probably a typical number to use if you're really, your capacity is really sensitive to the compressive strength of concrete adopted. You might want to use a higher 90 or 95% confidence level, and you can see the K values increase quite markedly for small numbers of specimens for the higher confidence levels. By the time you get to a number like 10 or 20, they're not so sensitive to that. The Z value, which is applied to the uncertainty of the strength correction factors, is just taken from the normal distribution for the various confidence levels. And so you can plug and get an answer that way. Again, what you'd be saying is I've got this in-place strength, and based on the tolerance factor method, I'm going to get some equivalent specified strength such that I'm quite sure that 3 times out of 4, or a 75% confidence interval, or 19 times out of 20 for a 95% confidence interval, the area that's less than the equivalent specified strength is less than the 10% fractile. So the alternate approach says there's a lot of scatter. And so let's calculate the mean in-place strength. Let's calculate a lower bound on the mean in-place strength. Let's think about the typical within structure variability. And based on all that, let's then calculate an equivalent fractile. And for practical cases, you get a higher equivalent in-place strength than using the alternative approach compared to the tolerance factor method. Lower bound of the mean in-place strength. Here's the mean in-place strength. There's the lower bound. And you're taking Instead of just the standard deviation of the core strength, it's now the standard deviation of the mean core strength, so you're allowed to reduce it by the number of cores that you've tested, and this is now the value from the distribution. You're still accounting for the uncertainty of the core strength correction factors. There's the variation with T, and you can see that it's much less than the variation of K was. K for 3 specimens was a number like 2.5. Here it's a number less than 1. And then based on some studies that were done almost 20 years ago, we can say that the equivalent strength is equal to coefficient C, which accounts for the within structure variation, which is typically, if you've got many batches of test in place concrete, typically a number like 0.83 to 0.85. These are data from John Hansen's survey. He posed the question to say, here are 10 core strength test values. And as you look at those numbers, it's a beautiful data set because there's one number in there that is arguably an outlier. Most of these numbers are between 3,800 and 4,400 psi, but there's this one 2,500 psi number in the mix. Okay? This is chillingly realistic, unfortunately. You could ask yourself, well, is it an outlier? The core document talks about using ASTM E178 to decide whether you can leave it in. If you do, you get a mean strength of about 3,900 psi and a coefficient of variation of 15%. If you take it out, you get about the same mean, but the coefficient of variation drops remarkably. This, from my experience, would be a pretty darn good set of core tests if the core coefficient of variation was that low. Hansen collected 27 responses. The question was, what number do you use as the specified strength? He got 27 responses. 25 were from licensed engineers. You can see that the numbers varied between 3,000 and 5,000 psi. Okay, that's a lot. There was some tendency around 4,000. You can see there were some other people that kind of like 3,400 to 3,700. Okay. If you want to find it, there's the paper that Hansen wrote about it. If we look at the tolerance factor approach, we can see that I don't want to say that it's right to put that suspect value in or to take that suspect value out, but I would be making the point that you get quite different numbers. The decision about leaving it in or taking it out is quite a big deal. If you look at the alternate approach, then you can see actually that if you leave it in and you've got a high coefficient of variation, you get higher strengths using the alternate approach compared to using the tolerance factor method. If you throw it out and you now have a fairly low coefficient of variation, you actually get higher results using the tolerance factor method. But I would draw your attention to this column, which says, you know, the results that you get are not nearly so sensitive to whether you leave it in or whether you take it out or not. And so I think that really one of the best reasons for using the alternative approach is that if there is a possible outlier in your data set, your results are much less sensitive to that. So, almost there. Conclusions. The first one is, again, to underline, please, that 214, Chapter 9 gives criteria for evaluating the strength of an existing structure using core data. Don't use Chapter 9 for checking strength compliance in accordance with ACI 318, Chapter 5. The criteria that are given in Chapter 9 account for both the uncertainty of the in-place strengths and the uncertainty of the empirical strength correction factors. And the 228 document does that, actually. That was the guideline for 214. The procedures both are intended to yield equivalent to specified strengths consistent with customary resistance factors as the 10% fractile of the in-place strength. And the alternate approach is much less sensitive than the tolerance factor approach if possible outliers are present and you're not sure whether to exclude them from the data set or include them in the data set. I would like to acknowledge a whole bunch of people from ACI 214 and core report task force members, Ron, Alfred, Brian, and Woody, who helped tremendously. Jim McGregor had a fair hand in this 20 years ago, and funding from NSERC and other sources. And if there's time, Mr. Chairman, I'd be delighted to take questions now.
When you're rendering the variabilities of each of the individual factors,
Yep.
in some of your squares, is it considered correct or incorrect? Do you have any comments with including the variability of the test, the test itself? Like, when you're doing a compressor strength test, there's a certain single unit variability within the test method.
That's a very nice question, and that we're going to have to think about for the next edition of this standard. Right now, it's not in there, and I think right now, core strengths are so variable that if you were to include that or not include that, you probably wouldn't get a terribly different result. So the way these standard deviation or coefficient of variation calculations work, it's like a vector addition. And as long as you've accurately got the biggest vector that you need to be accounting for, if you forget one, well, the change in length of the final vector isn't sensitive to that relatively small. Good, thank you.
Good afternoon. I'm going to share with you the experiences that we had and some test data on doing some high-strength concrete down at rebuilding the World Trade Center, in particular what was called the Freedom Tower and is now called Tower 1. We had concrete strengths there of up to 14,000 psi and 14,000, 12,000. And at 14,000, in addition to that strength, they also wanted a modulus of elasticity of 7 million. So we did some coring, and one of the main reasons we did coring is because Al Kaufman told me don't core high-strength concrete, so then I knew I had to core it. But actually, we did core it because there were some issues that we had, and we were just trying to figure out what was really going on. And this whole issue of this 0.85 came into effect. Now, the mention was made before about 0.85 dividing the core strength by that gives you the cylinder strength. Actually, many engineers in the New York City area take the core strength, divide by 0.85, and say that is the actual strength of the concrete in place, which it may or may not be. I'm not here to say it is. I'm just here to question whether, in fact, that 0.85 really does exist everywhere. I don't think it does. All the test data that I'm going to be showing you has to do with 4-inch cylinders, comparing 4-inch cylinders to 4-inch cores. So we took that out of the equation, the different size cores versus different size cylinders. Here is Tower 1, which used to be called the Freedom Tower. It's up to the 62nd floor right now. This is looking at it from the south, looking north, and here are the footprints from the original towers 1 and 2. Okay, and again, here's a close-up of the World Trade Center site as it's under construction. Now, this was probably taken a month ago. You could see more. You could see better the footprint of the North Tower, the South Tower, and this memorial. At least at grade will be open this September. You see Tower 4 going up here. You see work on Tower 3, work on Tower 2, and this is the Memorial Pavilion. So things are really cranking up down there. And here's a closer view of the 2 footprints. These are granite lined, and water will be cascading into these basins once this is opened, and the names of the people that perished at this site will be engraved on the side of those pools. And here, a close-up of that site, and here's a close-up of those pools. Here is the memorial below grade. Again, the foundation of the tower. Here was where Tower 1 stood. This is the tiebacks. That's going to be part of this subterranean pavilion for the World Trade Center. And again, that should be opened in about a year. And here is the pavilion for the memorial. Here are some of the arches. The steel arches are stupendous that are going in there that will lead up to the memorial from the hub and also from Tower 1. So this was going to be concrete, but the concrete industry didn't seem to be too interested in doing these arches, so we went to steel. Okay, here we go. Here's our conclusion. I'm going to give you my conclusion before I show you any data. After coring and testing, we came to the conclusion that perhaps the core data that you get is really what the strength of the concrete is in place when you really slice through it. And there are many reasons why it's different from the cylinders, and that the cores would agree with the cylinders, I think, is just an oddity for the most part. I mean, I think the probability of the cores agreeing with the cylinders is not very good for a variety of reasons. And I'll go into them. And again, here's 318. 318 states that you can accept concrete based on drilled cores, which is fine. Nothing wrong with that. And when you drill these cores, you should take these cores in accordance with C42. You could play all sorts of game with cores, and if you're really going to use this in any way, you should really stick to ASTM C42, strictest sense of the word. And again, ACI says that if the core data is at least 85% of F prime C, they would recommend accepting it, and if no core was less than 75%. And again, I don't really have an issue with this. The only reason why we started coring more is because our some of the engineers that we had working for us would take the core data and divide it by 0.85, and I'm not sure if that's accurate at all. Okay, why do we have, in general, lower core data? Okay, or at least that's the perception. Well, for one, I guess the idea is maybe the maturity of the concrete in place is different, and that's true, especially during the winter months. But for the most part, maturity is not an issue. The maturity of the concrete in place usually far exceeds the 28, 56-day breaks by the time we get around to coring. You know, we usually have 1 or 2 meetings where we exchange blows, and then we go and we core. So it's not 56 days. It's usually, 120 days. So I don't think maturity is an issue. Size of the cores, yes, that's certainly an issue. If you take small cores, you certainly build in a lot of variability. So if at all possible, we should use 4-inch cores. Damage to the cores, yeah, I guess there were papers written in the past where people found that there were damage to the cores, and they showed that certainly would affect the strength of the concrete. I'm not debating that. The only thing that we questioned whether if we have 16,000 PSI concrete, how much damage are we really causing to the cores? And that's what we got into trying to figure out what's really going on with these cores for high-strain concrete. We think part of the reason for having different strength in place is, number one, curing. Okay? We cure cylinders in accordance with C31. When was the last time we cured the concrete in place in accordance with C31? Never. Okay, never. And, as an owner, we really don't take too much comfort in that the cylinders are good, but the in-place concrete stinks. Okay? Really we're more interested in, well, what's the concrete in place? Just take a look at temperature. When we have high-strength concrete, we say that you must cure the cylinders in the field at 68 to 78 and take them to the lab and cure them at 73 degrees. A lot of this high-strength concrete in the field could be cured at 160, 180 degrees the first day. Do you think you're going to get the same strength in the field as you got in those cylinders? Okay, and that's not unusual. Curing. What kind of curing do we do to high-strength concrete? I know in New York City, if God's not cooperating with rain, it don't get cured, That's really the kind of curing we have. Consolidation. Okay, we have self-consolidating concrete. Well, I tell you, self-consolidating concrete certainly does help. There's no question about it. And on this particular job where we had the 14,000 PSI concrete, it was, we didn't call it self-consolidating concrete, but the spread on this, there was no slump. The spread was 25 inches. So I guess you could call that self-consolidating concrete. But we certainly did consolidate it also. And I got to say the concrete did come out very good. It looks good. There's very little cracking in the whole bit. Now, coring. Yeah, I guess you could damage it to coring. There's no doubt about that. I would certainly not debate that. Maturity, again, maturity could be an issue if it's during the winter. But again, other than the winter, I don't think maturity is ever the case, meaning that the maturity of the concrete in place is less than the cylinders. It's usually the other way around, that the maturity of the concrete in place far exceeds 28, 56-day breaks that you have. That's never an issue. So what is the issue? I think this is a big issue, and this is a big issue for the cores in place, and it's not damage to the cores. Okay, when we got involved with this Freedom Tower, we knew that in New York City, we love to use a lot of cement and cementitious material in our concrete mixes, so we put in a specification that in-place temperature cannot exceed 160 degrees, delta T 35. So, why did we do that? Because we did not want 1,300 pounds of cementitious material, and we were no one would accept that. And before we accepted a mix design, we said to the concrete contractor, you must cast a block. We know there's a lot of programs out there that can predict the temperature of the concrete. We want you to demonstrate to us what is the temperature of this concrete. Why? Because the core of this tower was as thick as the shear walls in the core of this tower were as thick as 6 feet. That's certainly mass concrete. And if you put concrete mixed together that has a high cement factor, you're going to cook a lot of that concrete. There's no question about it. So we said, you're going to demonstrate to us that you can get this 160 degrees and in a block of concrete. So anyway, I'm going to show you some results from this mix here and this one here. Here we had a total cementitious of just over 1,000, about 700 pounds of cement, and this one here, total cementitious 820 and 300 pounds of cement. And here's what we did. We actually cast these blocks. They were 6 feet, 8 feet by 10 feet, and we would put thermocouples in them, and we measured the temperature of the concrete in. These are core holes that we, after the fact, decided, hey, we got this concrete sitting out there. We got nothing to do during the winter. Let's go poke some holes in and see what kind of strength we got out of that. And that's what we did. So anyway, here is the temperature profile. Now, this was done in June, okay? So concrete showed up on the job at about 75 degrees. And notice the mix that had 700 pounds of cement. We peaked at 182 degrees in 24 hours. That's not good. That's not good at all. Now, again, there's a lot of concrete out there that perhaps does that. This one here with 300 pounds of cement peaked at 162 degrees, but it took almost 2 days to get there. So we said, we'll take that one. We'll take the 162. Now, let me show you some core data from these two. And here's what we did. We actually took a vertical core in the middle of the slab, one foot from the edge, and we took some horizontal cores. Again, reading the 214 document, horizontal versus vertical, center versus edge. Is there a difference in the results? And again, we're the Port Authority. We collect tolls, limited resources. Let's core away. And here's what we got. Okay? Now, this is the one with the 820 pounds of cementitious material. Peaked at 162. Okay? Vertical cores. Edge, center. Basically the same results. Horizontal. There wasn't much difference in the results. Taking testing error. Basically, the horizontal, the vertical, the center, the edge, there was not much difference. Okay, what did we get with cylinders? Here's what we got with the cylinders. 56 days, 17,290. What did these cores produce? 15,780. Okay, were these cores damaged? I don't know, maybe not. I don't think they were. I think that's really the strength of the concrete in place. That's what we got. Why? Well, maybe because it was the temperature. Maybe it was the curing. We certainly didn't cure this concrete at 68 to 78 degrees and 73 degrees for 56 days. We didn't do that. Okay, it was certainly hotter than that. So did we take away from it? Sure. But 9%, no big deal. I mean, if you really design these mixes in accordance with ACI 318 and you over-design for F prime critical, you're really safe. There is nothing much to worry about. Okay, you don't get what you got with your cylinders, but you're certainly not compromising anything with the structure. Here's one for you to worry about. This is the one with 1,000 pounds of cementitious material. This one peaked at 182 degrees in less than 24 hours. Look at these strengths. Look what the cylinders got. 18,140. This is a 30% reduction in strength. Look at the variability in these cores, right? Mike talked about variability. What do you think about this variability? Not too variable. Huh? And this was about 40 cores that we took. Again, we're the Port Authority. We can cause till we're blue in the face. And here, this was tested at 173 days. What do you think the maturity of that concrete in place was? It was better than 56 days, trust me. Okay? So, what's the moral of the story here? Okay? That's what you got. Okay? Don't give me this 0.85 factor. This is what you got. If you don't believe it, okay. Take your 0.85 factor. And again, that's what our engineer would keep doing. 0.85 factor. ACI 318, 0.85 factor. Okay, use it. Okay, and here's the actual mix that we used. Okay, we adjusted it. We put in about 50 pounds more slag from what we started out with for workability only. One of the problems that we find is that we tend to add cementitious materials for workability, now on our jobs, and not so much for strength. And here we go. This was a blend of number 8, number 6, and 7 stone, 0.25 water cement ratio in air, less than 2%. Okay, in air, of course, for high strength concrete, very important, keep it low. And of course, 0.25 water cement ratio is, very low. Okay, here are the results that we got. And the concrete producer did a fantastic job. Okay, here's what he averaged. Here's the standard deviation. That's the coefficient of variation. If you go by ACI 214, okay, this is excellent. Somebody would say, this data looks made up. It's We tested this. We do all the testing. There's nothing in it for us to make up data. We don't get paid any more, whether the coefficient of variation is 7 or 17. Okay, that's what it turned out. But I tell you, the same concrete producer can give you a coefficient of variation of 14 for 5,000 psi concrete. Okay, what's the moral of the story? You got to pay attention to what you're doing. Okay, and when he did, he produced fantastic, consistent concrete. Here's the margins of elasticity, 7.5, not too bad. Air content, great. Water cement ratio, 0.29. Now, that 0.29 is not make-believe, okay? We actually do the microwave test. I know there's people in the audience here that don't like it, say it doesn't work. It works. It's a great test. We use it all the time. And it gives you a good reality test when you're doing high-strength concrete or concrete that you want durability for. Where am I? Do I have a problem? And there were many times when we call up the concrete producer and say, you better take a look at your water. Your water's high. You're going to get in trouble. And you know what? They did on occasion, and they corrected a problem. On occasions, they didn't, and they paid the consequences. The consequence of the Port Authority job is that we have an end result specification, okay? And here's what we want, and we want 95% of the concrete to be above 14,000. If you dip below 95%, we then reserve paying you full amount. We reduce payments on the price of the concrete, not in place, by 50%. We also give a bonus of 6%. So, we don't have too many Boy Scout stories to tell, getting together at meetings, what went wrong, the phase of the moon was off, that's what I'm going to do. You know, that doesn't enter into the picture. You say, by the way, you got 50%, you better get your act together, that's what you got. And, you know, we do get together, and then things sort of go, and they go the right way. So, I'm a firm believer in end result, but put a little incentive in there. Give the good concrete producers something to shoot for. Okay, Corey, here's some cores. Right out of that tower, what happened? One day we were placing concrete, the concrete contractor said, this is moving too slow. We were pumping 30 yards an hour, okay, which is slow. That is slow. So, the concrete supplier decided to put more air in the concrete. You know, you fluff it up a little, you pump a little faster. The air went up to 4%, and his strength went down quite a bit. Cylinder strength was 14,570. Not a problem, not a big problem, but it wasn't 16,000, 17,000. So, and our inspector noticed a lot of foaming on the top of the pour, so we decided to pour the concrete. The worst thing we ever did. Look at this. 10,600, so that was at 57 days, okay? We came back a couple of weeks later. Not much change. Came back at 83 days. Not much change. That's what we got. Now, these cores they did not look good. The consolidation did not look good. And that maybe was the strength of the concrete in place. But the engineer of record was able to really take care of this whole thing. He divided that number by 0.85, and then he did some more massaging, and it turned out okay. So you have to ask yourself, did we really need 14,000? Okay, so we know we always core when we have a problem. Oh, then of course we say, hey. I said, we got a good core here. Here, cylinders, 16,670. Let's core a good one. Let's see what happens if we have some good concrete. Let's see what kind of results we get. Well, and here's the depth factor, 6 inches, 12 inches, 18 inches. It really didn't change that much by depth, okay? And when you add this all together and average it out, average core strength was 14,100. This is the cylinders that was 16,670, okay? Interestingly enough, that was reduced by 15%. Now, nobody should write this down as this justifies the 85% cut. Okay? This is just coincidental. But anyway, that's the way it turned out. Now, this was a good pour, no problems. We just decided to core it to see, hey, what do we have here? And, of course, we were expecting to see something close to 16,000, not 14,000. But these cores did not look all that great. You know, the consolidation was not stupendous. All right? Now, that concrete producer was given the heave ho by the concrete contractor for whatever reason, and they brought in another concrete producer. Okay? And the first day that he supplied us 14,000 psi concrete, we said, hey, you're a little high on the water based on our microwave testing. And not that it's cataclysmic, but you're a little high, you better watch what you're doing. Well, he did it, and basically the cylinders came in at 14,200. Okay, which is not the end of the world, but that gave him a 50% payment, 50%. So he said, well, I want to pour because his cylinders were better than ours, and he said, okay, we'll pour. So we got together, we agreed where we would take the pours. They were there in fact, they poured it. We just witnessed it. And we brought them back to our land. We prepped them. They witnessed the bringing of the pours. And the cores actually broke at 13,830. Basically the same as the cylinders. You know, a few hundred PSI, and what's that among strength? Nothing. Okay? So we got the same strength in place as we did in the cylinders. Those cores look very good. They look very uniform, well consolidated. So again, the point I'm trying to make here is that, you know, maybe what you get in those cores is maybe what you have in place. Okay? And, you know, you could do all the arguing you want, but that's what we found. So we said, well, you know, let's take a look and see, is there this, you know, factor for damaging the cores? Let's pass some slabs in the lab. Let's core these slabs and see what we get. So that's what we did. So here's the slab. Okay, and what we did in addition to that, we said let's put some cylinders in these slabs also. Okay, so that will be a control. In other words, these cylinders will be curing at the same temperature, and then we'll test these and we'll see how these compare to the cores. Not that we knew where we were going, but that's what we did. Okay, but anyway, these slabs were cast, and some of them were cured. I'll show you. Some of them were cured in the lab, not moisture, just at lab conditions. Others were cured in the moisture. And others, we also tried to mimic what we got in the field, 160-degree temperature. And we tried to get the concrete up to 160 degrees in 24 hours or 190 degrees to see what detrimental effect that would have. With the 300 pounds of cement in the mix, we couldn't do it. Okay, we could never get the strength of the concrete, the temperature of the concrete to peak at 160 or 190 in 24 hours. It took about 2 days before we could get there. But anyway, I'll show you that data. So actually, and here we are outside our lab, coring that slab, and here's the data. Here we had a block that was, this was cured in accordance, everything here was done in accordance with ASTM C31, right here, normal, okay? But, again, this is the data we got. There was something wrong with these cylinders, okay? These cylinders broke very low. So I asked the guys, what did you do to, you know, and of course, nobody did anything wrong, but of course, they are no good. I don't believe these numbers here. Compare them to the cores that we took out of that block. Okay, now again, same concrete. We made a block that we cored in 56 days, and here are the cylinders. So these numbers are not good, but again, sometimes you do have bad tests. And again, I'm just sharing that with you here. Here are the cylinders that were cast in the slab. Consistently, these strengths came out the lowest. They were much lower than any of the coring that we did. Okay, the cores did not come out all that bad. I mean, they were a little lower than the cylinders. Here's cylinders that were made in accordance with C31, but they weren't moisture. They were cured at room conditions. Okay, so here's what we got at room conditions. Here's the cylinder that was cured in the slab, and here's the core from the slab. Here's again the same concrete that we tried to get the temperature of the concrete up to 160 degrees in 24 hours, what we could, and they got up there in about 2 days. And here's what we got out of the cylinders, and those cylinders were also put in that same bath that we tried to get this elevated temperature. Same with this block, and the cores, which we took out in 56 days. And again, once we did this with this temperature for 2 days, then we cured it in the moisture. All of this was cured in the moisture, okay, for 56 days. These are all 56-day breaks. And then again, when we attempted to get the concrete temperature up to 190 degrees, which we were not successful in doing, here's where we got the cylinders, again, C31 cylinders that were cured in the slab, and cores taken out of the slab. If you take the average of these, if you take out this, if you take this one out, and I think there's something wrong with these cylinders without a doubt, we average cylinders 15,790. The cores average 15,350. Not a significant difference. Okay, you know, hardly anything to argue about that there's some great damage to the cores due to coring for this particular concrete. Okay, and the standard deviation was not too bad either. So that's what we got when we tried to find out how much are we damaging these cores, and how much of this reduction in strength should be attributed to coring. Based on this, not a lot, assuming that the cores were done reasonably well. Here's the temperature curve. Again, when we tried to get the cylinders in the slab at 160 degrees, and basically it almost took us 2 days to get there. So, and again, we tried to mimic here what we had in the field. And in the field, for this, the mix produced about 16,000, and same here, about 16,000. And again, the 190 was about the same, although the cores were a little lower. And again, that's the temperature profile for the 190. And again, we didn't get there for 2 days. Okay, so What's the gig here? We think that a lot of the poor cores that we get are probably just due to, poor consolidation, temperature at which we're curing the concrete, and certainly lack of hydration, perhaps. I mean, these mixes here, again, why were the cylinders that were cast in the slab, why did they consistently produce the lowest strength? Is it because they were starved for water and they didn't hydrate as much as everything else? I don't know. But it's interesting that the cylinders, again, that concrete was cured in a cylinder for 56 days. They produced the lowest values. Okay. We don't think there's much due to coring. Now, again, we're talking about high-strength concrete. We don't think that the reduction in strength, much of that is due to coring. We think that most of it is due to this here. And again, temperature. For high-strength concrete, if it's mass concrete, certainly if the temperature shoots through the sky in the first 24 hours, you're going to kill the strength. And again, in those blocks, we showed that when we hit 182 degrees in 24 hours, we cut the strength by 30%. So we think those are the reasons why the cores don't match up with the cylinders, and perhaps, we're not getting. The troubling thing about this is that, it's nice that we pay a lot of attention, or we pay more attention to making cylinders, but how about paying a little more attention now to the high-strength concrete that we're casting in place? I don't see anybody worrying that the temperature of the concrete in place is too high, or it's not being cured, or it's not being consolidated, People seem to go, well, how are the cylinders? But that's the way it is. And again, I think it should be an eye-opener for all of us. We should use high-strength concrete, no doubt about it. It can be done. It can be done successfully, without a doubt. Without a doubt. But, we have to keep in mind some basic principles of concrete that we don't screw it up. Okay, we don't want to screw it up. Okay, thank you.
This presentation that I have is on the application of the Chapter 9 section of the 214.4R document. This building is a professional building. It was designed in the late 1920s and was put into service in 1931. It was occupied and served as a professional building, doctor offices, dentist office. I think there was a bank that occupied the lower floors at one time. And it was occupied continuously until the early 90s. At some point just before the turn of the century, we had somebody purchased the building and was going to modify it and convert it into high-end hotel, condominium kind of facility. So there's 13 stories of reinforced concrete. The rehabilitation did start in 2008, and believe it or not, as the economy kind of tumbled, the project stopped and project went into bankruptcy. So I can't tell you how all this turns out, but I will be able to tell you. You have to come back next year. I will be able to tell you how we went through to help out an engineer in this. The type of construction, it's a slab and joist type of construction. We were asked by a contractor who was being asked by a fire protection engineer what F times of C is of the concrete that's in place. And he wanted to have some idea, so can you go out and get some cores? And of course, we know of the existence of this ACI document, so we broke out that document and we established a coring program in order to be able to give that information to him on F primes at C for his fire protection work. They were also interested in knowing what the unit weight was and the thickness of the concrete. So we devised a sampling plan that followed the ASTM E22 for the number of cores per floor. And in a minute here, I'll discuss a little bit about how we got there. This is the equation that's given in E122. It's also mentioned in the 214 document. And if you notice here, there's two variables that you plug into this equation. These are obviously equivalent. What we did was make a guess that the maximum error we could live with was 500 psi, and that the estimated standard deviation is 500 psi. And I'd like to say that we made that after giving considerable thought and research, but we dated that so that this number would be 4. And it turned out to be 4. The maximum error you can tolerate, we weren't quite sure. We did believe that concrete having a standard deviation of about 500 psi might be a reasonable number. And if you play around with those numbers a little bit, you can get an N here that gets pretty large if you let this number get ridiculously low, or if you let that number be ridiculously high. We also were fairly confident that since this structure was built at about the same time, that there wouldn't have been a lot of variability, and actually all of that concrete is the same concrete. And we ended up with a population of 51 cores, which would far exceed any number that you get with this plugging in other numbers. We wanted to have at least 4 cores from each one of the floors so that we could do a little bit of comparison to validate whether there was a difference among the floors in the structure. This 2 number, if you look at E122, comes from the number of standard deviations that you may want to be away, and it does give you some guidance that you can use a lower number, and we use 2, and I think our document uses 2 as well. So, like I mentioned, we ended up with 51 cores taken out of the structure. There were 3 or 4 cores that were rejected that aren't included in the 51 count that were rejected in the field. My colleague, Dr. Tixier, was in the field while they were coring, and we wanted to make sure we had sufficient core length to at least have a one-to-one L over D. And so if the core length is right at 1/1, you don't have the ability to trim. He rejected some of those, but we ended up with 51 cores. 4 of those cores, after we did get them into the lab, had insufficient length for us to test, so we didn't even test those. And there were 12 of them with wire reinforcing. They were either rebar or some small wire, and we tested those, and we got compressive strength values from them. And we ran a student T evaluation to see if the cores with and the cores without wire were the same population, and we concluded that they weren't. So we threw that data out. We didn't include that in the summary. It turns out that the cores with the wire reinforcing were significantly higher at a 95% confidence level than the cores that didn't have any wire reinforcing in them. When you look at the overall distribution of all, there would have been 47 cores that were left. 47 cores, it made a fairly reasonable approximation of a normal distribution curve, the John Paul Jones hat, I call it. When we excluded those, it was truncated. So this part of the curve was kind of missing, but we felt like we were excluding higher data, and we were being a little more conservative by not including that higher data. So we felt very comfortable in rejecting the cores with wire and reinforcing in them. This is all of the data that we had, and this is summarized by floor. And if you look at the averages here, they look fairly consistent. This is the floor. All of these had reinforcing in them. So in the final assessment, there's no data for 6 because we rejected all of those. And I'm not sure what happened to that guy. But this data looks like it's fairly consistent. And here's a chart. The blue color there, the lighter color, is the average of all the cores by floor. And then the cores that were remaining after we were done. So you can kind of see we biased the data to the lower side as far as the average goes. So the summary of the coring that we did, the average diameter was about 2 3/4. It was a nominal 3-inch hole, and you end up with about a 1/4 inch less when you're cutting the core. We used that because we weren't sure exactly how thick it was, and we wanted to be close to an L over D of 2. The average length of the cores, you can see there, quite a bit of range. We had an average unit weight of about 143 pounds a cubic foot. Without adding any kind of correction, the average of the cylinders that we used in the testing was about 5,600, and it had standard deviation of twice what we had estimated when we did our calculating the correct number of cores to take. And I'm really glad Mike went first because he explained these things fairly well, and so I'm not going to spend a lot of time, but we did use the factors that are in the document to computate or to compute this F sub C number. There's a compensation for the L over D. There's a compensation for the diameter if it's different than 4 inches. And there's a moisture condition factor that you can use, and then the damage that has been talked about here by a couple of us. These are the tables from the document. We use the standard treatment equation in our calculations because we did use the standard treatment being what ASTM C42 discusses. Our cores diameters were in between those two, and we did just a interpolation between those 2 points to come up with the factor for the L over, or for the diameter. Our moisture standard treatment is a factor of 1, and then we use the 1.06 factor for the damage due to coring. And when we were done with all that, we plugged those numbers into this equation and came up with the average for the core of about 5,800. And this is the untreated, the raw data culled. In other words, when we left out the cores for the rebar and the ones that were too short. And then the final data after we apply those factors. And there really isn't much of a difference between those numbers on any of the floors or collectively. For those of you who love data, this is all of the data by floor with the standard deviation by floor. You can see we increased in some areas we increased our variability by eliminating the cores with the rebar, and in other places we reduced it. This one got reduced to infinity or 0. And again, what's left in the data seems to be a fairly reasonable set of data to then move forward to calculate an F prime sub C equivalent. Mike talked about these uncertainty factors. We did go through and calculate those using the tables in the document. Variability, these are the coefficient of variations that go in that previous equation, and they're just related to the numbers that you chose to arrive at your original correction factors. Mike also talked about the 3 levels of confidence, ordinary structures, 90% for very important things, buildings, and 90%, 95% for critical applications. We didn't get any of that information from the fire protection engineer or from the contractor who asked us to do this work. So I'll show you how we resolved that particular issue. Again, the 2 approaches that are outlined in Chapter 9, there's the tolerance factor approach and then the alternate approach. This is the equation for the tolerance factor approach. At this point, the data that we've collected and talked about has all of those except for these 2 factors that come right out of the table and get applied in there so that you can come up with this F prime sub C equivalent. And in the alternate approach, it's the same thing. There's some factors that go with it. The summary data from the coring has all been done and calculated, and then it's just a matter of plugging the data into these equations to arrive at an equivalent F prime sub C. That's the summary of the data that we arrived at. And it's kind of surprising. There's very little difference in the 2 approaches. And I think Mike mentioned that the higher the variability, the more forgiving that this one was. I can't remember quite how he said that. But you can see that at each one of these levels, if you want the 95% confidence, these numbers are almost identical. These are almost identical, and these are almost identical. Both of these methods are actually very easy to calculate once you understand the data that has to be gathered. Probably the most important thing is to make sure you have a large enough sample size. Using that equation, if we went backwards from what we had up to the fact, or accept as fact that there isn't any difference among the floors. Our population sample, we ended up using a total of 35 of the data points. Our population sample was very sufficient to have the 10% confidence that this number, if you remember Mike's distribution curve, 10% of your shrinks might be below that, so you have the 90% confidence that you're higher.
All right, any questions?
How did your density test compare to your breast strengths?
Yes, I did. There was no correlation between. I was surprised at that. My colleague, Dr. Tixier, doesn't believe that there is much of a correlation between unit weight and standard strength concrete and compressive strength. But it was rather scattered. There was a little bit of if you did a linear regression, there was a little bit of a trend line that followed the data appropriately. So the correlation was very poor. I think it was less than 0.3 per R squared.
Base your density does not weight of the core, or did you do submerged weight?
I believe we used our measurements after saw cutting. We've done that both ways too, and I was awful surprised because I thought I was going to show somebody how much more exact it was to weighing submerged, and boy, they're almost identical. Well, thank you all very much.